Energy could neither be created nor destroyed. In any system that we talk about, this is true. In fact, it is always true. The energy created in the Big Bang is still around today. It's just spread out more and changed form. That's what happens in our oscillating systems. In our simple harmonic oscillator, we ignore resistive forces. This means that the only energies in our oscillating system are kinetic, or moving energies, and potential, going to become moving energies. The system works by constantly changing from one form of energy to the other. All oscillating systems behave in the same way, so it doesn't matter if we talk about a mass spring system or a swinging pendulum. In a mass spring system, the potential energy is stored in the extension or contraction of the spring about the equilibrium position. In a pendulum system, the potential energy is stored in the height the bob reaches above the equilibrium height. Either way, the energies are linked to the displacements and velocities of the objects oscillating and always add together to reach a constant amount. Kinetic energy in a system plus potential energy in the same system add together to equal a constant value. If we know the total energy of a system and the kinetic energy of a system at a given time or displacement, we know the potential energy as it is the total amount minus the kinetic energy. Let's look at how energies vary with displacement and time. Kinetic energy is equal to half mass times velocity squared. We're not interested in exact values here, so we do not need to use the equation in full. We know, however, that kinetic energy is linked to velocity. The higher the velocity, the higher the kinetic energy. At the maximum positive displacement, the velocity of an oscillator is zero. Therefore, the system at this point has no kinetic energy. All the energy of the system is therefore stored as potential energy. In a pendulum system, you could work out the total energy of a system by measuring the gravitational potential energy at this point. Gp equals mgh, where h will be the value of the maximum displacement. In an oscillating system, we start oscillating at maximum positive displacement. So at time zero, the potential energy is at a maximum and the kinetic energy is zero. When a displacement away from the equilibrium position falls to zero, we have the maximum velocity of our oscillator. This means that the energy of our system is completely in kinetic form. There is no potential energy involved. The first time that the oscillator crosses the equilibrium position is a quarter of the way around the oscillation. So if we allocated the time 0 to the maximum positive displacement of our oscillator, then the time when the potential energy has first reached 0 happens when the oscillator has completed a quarter of its time period, or t divided by 4. The displacement now moves into the negative and slows down until it reaches the maximum negative displacement. Here the oscillators stop, and so we have no kinetic energy. This means that we have maximum potential energy when a displacement has reached its maximum negative value. This is at time period t divided by 2. The same pattern repeats. When displacement returns to equilibrium position, the velocity is at a maximum, and so potential is 0. This is the same as at time 3t over 4. On completion of a full cycle, time period equals t, the displacement is back to its maximum positive value. Velocity is back to 0, kinetic energy is also back to 0, and potential energy is at a maximum. Looking at it on a graph, you would need time and displacement along the x-axis, and energy on the y-axis. There is no need for a negative part of the graph, as energy is not negative. You could have a line across the top of your graph to represent total energy. This value does not change as energy does not enter or leave the system. At time 0 displacement, displacement is maximum, positive, and potential energy equals total energy. Between time 0 and time t over 4, the potential energy decreases as a square of negative sign because kinetic energy is velocity squared, and velocity in a simple harmonic oscillator follows a negative sign function. As the potential energy decreases, the kinetic energy increases, so potential plus kinetic energy equals total energy. At time t over 3, the oscillator has no displacement and maximum velocity. The kinetic energy of the system equals the total energy, and the potential energy is 0. As time approaches t over 2, the kinetic energy decreases following the negative sign squared function of before approaching 0. And the potential energy increases so that kinetic plus potential equals 0 until at time t over 2 the potential energy equals the total energy. The displacement is now at its maximum negative value. Next, the time approaches 3t over 4, and the displacement is approaching equilibrium again. The velocity is increasing again up to total energy following a negative sign squared function, and the potential energy is decreasing so that potential energy equals total energy minus kinetic energy. Finally, the system goes back to how it was at the start. At time t, displacement is maximum positive, velocity is 0, kinetic energy is 0, and potential energy is equal to total energy. Looking at just potential energy against time, the curve follows sine squared pattern so that it peaks at time 0, t divided by 2 and t, and is 0 at times t over 4 and 3t over 4. Kinetic energy is the opposite, following a negative sine squared pattern, peaking at time t over 4 and 3t over 4, and is 0 at time 0, t over 2 and t.